Have you ever stopped to think about why a diamond is so hard, but the graphite in your pencil is so soft? I mean, they're both just carbon, right? Well, the secret isn't what they're made of, it's how their atoms are arranged. So today, we're going to take a journey into the invisible world of crystal structures, the atomic architecture that defines literally everything around us. Okay, just look at this. On the left, you've got quartz. It's a crystalline solid, and you can see its atoms are in this perfect repeating pattern. It's got long-range order. But on the right, that's glass. It's amorphous. And here's the crazy part. It has the exact same chemical makeup, silicon dioxide. But its atoms are just a complete jumbled mess. And that one single difference is why quartz is strong and melts at a specific temperature, while glass is brittle and just kind of gets soft when you heat it up. So yeah, that's the big question we're tackling, isn't it? How can the very same atoms build such wildly different materials? And, for anyone in engineering, the really important question is, how do we get a handle on this atomic architecture so we can start designing the materials of the future? To even begin to answer that, we need to learn the language of crystals. We got to understand their fundamental blueprint. This stuff is the absolute foundation of materials science. To get that blueprint, we start with this abstract idea called a lattice. Just picture an endless 3D grid of points. Now, this isn't the crystal itself, not yet. It's more like the mathematical scaffolding that we're about to build upon. All right, so now we take our scaffolding, and on every single one of those points, we place our building blocks. That's what we call the basis. And the basis can be super simple, like a single copper atom, or it can be more complex, like a whole group of atoms. So we have our scaffolding and we have our building blocks. The smallest little chunk of that combination that you can just copy and paste over and over again to build the entire crystal, that is the unit cell. It is the fundamental Lego block. And believe it or not, all of these possible combinations fit into just 14 unique arrangements, which we call the Bravais lattices. So if you remember one thing, remember this simple equation. You take the abstract scaffolding, the lattice, you place your atoms, the basis, onto every single point, and what you get is the final crystal structure. That's it. This is the core concept that explains everything else we're going to talk about. Okay. Now that we have the rules of the game, let's see how they play out in the real world, starting with metals. You see, metals really like to pack their atoms together as tightly as possible. It makes them more stable. Let's see how that desire for efficiency builds some of the most common structures in all of engineering. And for most of the metals you'll ever come across, their atoms arrange themselves into one of these three main structures. You've got body-centered cubic, or BCC, face-centered cubic, or FCC, and hexagonal close-packed, which we call HCP. Let's dig into what makes them different. To compare how well these structures actually pack their atoms, we use a number called the atomic packing factor, or APF. It's really simple. It's just the volume of the atoms inside the unit cell divided by the total volume of the cell itself. Basically, it tells us how much of the space is actually atoms versus how much is just empty void. Now this is where it gets really interesting. Let's compare FCC and BCC side by side. Right away, you see FCC has a higher coordination number. That means every atom has 12 closest labors, compared to only 8 for BCC. And look at the payoff. The atomic packing factor for FCC is 0.74, so 74% of the volume is filled with atoms. BCC is less efficient, down at 68%. This difference in packing is a huge reason why FCC metals like copper and aluminum are usually more ductile, bendable, than BCC metals. Those densely packed planes in FCC structures just let atoms slide past each other a lot more easily when you push on them. Okay, so we've got these complicated 3D structures. How in the world do we talk about a specific direction or a specific plane inside one of them? We need a coordinate system, kind of like a GPS for atoms. Well, we have one, and it's called Miller indices. Now, finding a plane's Miller index might look a little intimidating, but trust me, it's just a simple 4-step recipe. First, you find where your plane hits the x, y, and z axes. Second, you take the reciprocal of those numbers. Third, you just clean up any fractions to get nice, simple integers. And finally, you pop them in parentheses. Let's just try it with an example. Here's a really common one, the 11 plane. See how it slices through the x-axis at 1 unit and the y-axis at 1 unit? But look, it runs perfectly parallel to the z-axis, so it never actually hits it. We say that intercept is at infinity. So, let's take the reciprocals. 1 over 1 is 1, 1 over 1 is 1, and 1 over infinity is 0. Boom. That's the 11 plane. And here's another key plane, the 111. This one just chops the corner right off the cube. It intercepts the x, y, and z axes all at 1 unit length. So the reciprocals are just 1, 1, and 1. Easy. This is the 111 plane. And knowing about these specific planes is absolutely crucial because they often control how a material will bend or break. So far, we've been pretty focused on pure metals, but these same principles build our entire world of advanced materials. So let's zoom out a bit and see how this atomic blueprint scales up to create ceramics, alloys, and a whole lot more. Let's talk ceramics, like good old sodium chloride, table salt. The structure here is a little more complex. It's actually 2 Fc lattices that are interpenetrating, one for the sodium ions and one for the chlorine ions. And the key design rule here is the size ratio between the positive cation and the negative anion. That ratio dictates the whole setup and the stability of the structure. And alloys? Well, steel is probably one of the most important materials ever. It's what's called an interstitial alloy. We take the normal BC structure of iron and we sneak these tiny little carbon atoms into the empty spaces, the interstices, between the bigger iron atoms. This distorts the whole structure and makes it way harder for those atomic planes to slip, which is exactly what makes steel so much stronger than plain iron. And this brings us right back to where we started, with carbon. The ability of one element to exist in multiple crystal forms is called allotropy. When carbon atoms bond in this super strong tetrahedral network, you get diamond, the hardest natural material we know of. But when those same atoms bond in flat hexagonal sheets that are weakly held together, you get soft, slippery graphite. Same atom, radically different architecture, radically different properties. So why does all of this deep atomic level stuff matter? Well, look at this. This is a turbine blade from a modern jet engine, and it's grown as one perfect single crystal. Why would we do that? Because in a normal metal, the weakest points are the boundaries between all the tiny crystal grains. At the insane temperatures inside a jet engine, those boundaries would fail. By getting rid of them completely, you create a blade with a perfect, uninterrupted atomic structure that can handle unbelievable heat and stress. This is material science saving lives. And this idea of an atomic blueprint, this language of symmetry and repetition and order, it doesn't just build materials, it inspires us. You can see these very same principles at work in the incredible crystal-inspired architecture of designers like Daniel Libeskind. The blueprint really is everywhere you look. So, from the way a few atoms stack together in a piece of metal, all the way up to the design of a skyscraper, the fundamental principles are the same. Understanding this atomic architecture, it is the key to unlocking and designing the future of materials. So the only real question left is, what are we going to build with it next?